Quick note, this is an AI-assisted recap made for learning, not the original video, and not an official translation. Listen to a rich musical chord, a noisy recording crackling with static, or a detailed photo. All seem hopelessly complicated, yet each quietly hides the same beautiful idea. That idea is the Fourier transform. It answers one deceptively simple question: which pure, simple frequencies is a complicated signal secretly built from? The core idea: almost any signal you can imagine can be built by adding simple sine waves, each a pure tone vibrating steadily at a single, unchanging frequency. Pick the right waves, give each the right strength, and stack them up. Done carefully, even a jagged, messy signal emerges from smooth curves. This is superposition, the foundation of all that follows. If signals are just piles of sine waves, understanding one means finding which hide inside. There are two ways to view the same signal. In the time view, we watch its value rise and fall over time. In the frequency view, we ask a different question instead: how much of each frequency is packed inside this signal? Loud lows, quiet highs, and every subtle tone in between. Both views hold the same information in two languages. The Fourier transform is the translator carrying us between time and frequency, losing nothing. Here's the real puzzle: someone hands you a messy signal, with all of its pure tones already tangled together into one single wiggling line. How on earth do you pull them back apart? This is what the Fourier transform was built for: unmixing that tangled signal into its pure ingredients, like unbaking a cake into flour and eggs. The astonishing part is that it's even possible. From one curve, we recover every hidden frequency and its strength, no guessing. The trick works like this: wind your signal around a circle like coiling string, while you spin at one chosen speed, a test frequency. As it wraps around and around, the signal traces out a curling shape whose exact form is set by your chosen spin speed. Now watch its center of mass, the average position of the whole shape. For most spin speeds, the shape spreads evenly around the circle, so its center of mass sits right at the middle. Nothing interesting happens. But something almost magical happens at one special speed. When your test frequency exactly matches a real frequency hidden inside, the shape stops spreading out and instead bunches heavily onto one side, in resonance. Now the center of mass swings far from the middle. That spike is the signal shouting that this frequency is one of its ingredients. At every other frequency, the shape stays balanced and its center of mass rests near zero. A spike means a match, a flat reading, nothing. For the final move, we patiently sweep the test frequency across every possible value, winding the signal around again and again, and carefully recording how far the center of mass swings out each time. String those readings together into one picture, with a spike at every hidden frequency. That picture is the spectrum, exactly what the Fourier transform produces. Every spike names one pure tone buried in the signal, and its height tells you exactly how strong that tone is. Underneath the intuition, the spinning is clean mathematics. That rotation is just a spinning arrow, written as e to the I, from Euler's famous formula. A complex number is really nothing more than that arrow, carrying a direction and a length. Spinning it steadily equals winding your signal onto the circle at the test frequency. The whole transform is one recipe: multiply the signal by that spinning arrow, average, and repeat for each frequency. That average gives each spike's height. This deceptively simple idea quietly runs an astonishing amount of modern life: noise filtering, the equalizer sliders you drag in music apps, and the clever compression packed inside MP3 audio and JPEG images. It's inside medical scanners rebuilding the body, and the wireless signals carrying this video to you. Anything with sound, light, or data relies on it. There's even an everyday version: tap a watermelon, and your ear reads the frequencies coming back. One viewer joked it taught them to pick fruit. In the end, the Fourier transform is a new pair of glasses. Instead of the world changing over time, you see it as frequencies at once. That single shift in perspective turns brutally hard time domain problems into surprisingly easy frequency ones, uniting sound, light, and data. That's why this one idea reshaped modern science and engineering. If this sparked your curiosity, the original goes deeper with gorgeous animations, and its link is in the description. Go watch it. See you next time.